Hey Adriana. So I'm just gonna make this video, so it's a lot easier to explain it visually than writing a whole essay about uh, these two questions that you have. So the first question is how describe a situation where proxy geometry is used automatically to speed up simulations. We actually had done some RBD projects in class. So let's say we have a brick wall, and I'm gonna just make it a bit bigger, like so, and then we're gonna stick this to the ground or to the grid, and then we're just gonna run a ball through this thing here. But first we need to scatter, right? So we're gonna use point from volume. This is exactly how we did it in class in one of the first projects we had. I'm gonna just jitter this points a bit, make sure we don't have as many fractured pieces. And then what I'm gonna do now is I am gonna use Voronoi fracture node. Oop. And you see there's a bunch of points here, a bunch of fractured parts here. So what happens if I push the RBD button? I can play simulation. I'm just gonna fall down because we don't have a ground plane. There you go. So the sim is actually really quick, right? This is partly because we have a node called assemble. And John did explain this, um, but some people did find it a bit complicated. It's essentially just making it so, let's say you have a wall that's actually pretty complicated. We can use an exploded view here. So exploded view is just gonna split apart all the pieces so we can see them on an individual basis. So right now all the surfaces are just plain and boring, right? But we can do something very interesting with it. We can use a RBD interior detail. Let's see. So what this does, hmm, oh, is check this out. It creates interior details on the geometry. So now it kind of looks like, depends how much detail you want on it. Now we went from what, 1.1 thousand points to like 18,500 points. And each piece becomes pretty heavy. So the first pass simulation was pretty quick. The second pass kind of becomes heavier. And if we add more points, let's try it out. So we have to mess around with this thing here. So point separation. And there's a bunch of points. A bunch of interior details. If we simulate this guy, it's pretty heavy. So all the assemble node does is making the simulation go quicker. And that's why we have it here. There's a very practical example of how it's making it go quicker. So let's say we ignore this. I'm gonna just actually make a new scene. So we know that the shelf tool automatically creates a what's the word? It creates an assemble node, but we don't know why. Here's why. So let's say we have a kind of heavy geometry like the test geometry vertical. You can actually do it yourself and actually test it for yourself, by the way. So this thing here has 12,000 points. And if we use the assemble node, then all the colors disappear, but we'll only have 10 points. And these points represent each part of this toy. But if we use an exploded view, then we should be able to see the parts individually. So it's not one geometry. It's not what I mean. It's one geometry, but it's separate meshes. You have this, these three, and and so on. So we can use this assemble node to speed, or more like we can instance this geometry to speed things up, simulations. So let's add a null here. Pull this out, rub it away. And let's make it so it rains rubber toys. Just because why not? I'm gonna use the pop network node here. I do type very quickly, but I'll explain everything I do. So I'm gonna go to the pop source node and make sure it scatters on the surfaces. We get this effect. Oops. We need a gravity. And then we need a ground plane. Let's just merge this. So doing it this way is the same as using the shelf tool. We basically built the shelf tool from scratch, almost. So instead of using the collision layer, ground plane, we just manually added it to our nodes. We do this to give us more control over the network and the code. And we can just mess around it on our own conditions. I mean, in our own way. So now if we play this, the particles will bounce. I'm gonna just up this to 2 substeps and make the particles spawn a lot less and give it a 0.75 light factor speed with 0.25 light variance. Kind of get this nice effect here. I'm gonna just call this raining dust. And I don't want to see the ground plane. All I want to see is particles. So the simulations is fairly quick, right? It kind of goes in real time. But what happens if we do an object merge and grab the rubber toys? We use a copy to points to copy each of the rubber toys to each point in the pop simulation. And check this out. This is slow. You can actually see when the ducks pop up in the render and C view. You can see the FPS is really bad. The program is kind of chugging. So what is going on? Even though we've already cached this out, it's still really slow. The reason is because these three ducks are three individual ducks. I call them ducks because ducks, even though they're rubber toys. So if you look at the geometry spreadsheet, there's a bunch of points here. There's a bunch of info here. So we have velocity, life, and all that kind of stuff per point basis. 38,000 points. And if we just keep going, we'll have 334,000 points calculated, which is absolutely insane. But what we can do is we tell Houdini to assume this duck here is the same as this duck here is the same as this duck here again. It's all the same geometry because look, it's just one geometry. All comes from this one. So we can push different ways of doing this. We can push, for instance, this button here in the object merge, pack geometry before merging. Then this will happen. Check how fast it goes. We literally just answered the first question, which is how we can use proxy geometries to speed up our simulation. And this is basically our proxy geometry. Or this is more like an instance geometry. Now, proxy geometry basically is the same principle. So you know how you can create like a beautiful high polygon sculpt? For instance, beautiful high polygon sculpt. Like, alright, look at this. Oh, that's kind of scary though. Maybe this. Yeah, this one. Just look at this. All the polys here. This is super high poly. This is probably like a couple of million polys. Imagine simulate this many times. Or you not even simulate. Let's imagine that you want to rate this character in Maya, and then you're gonna animate this character. And if you have tried it with high poly, that's not gonna happen because if you want to move the arm, it takes forever to just animate a single millimeter of animation. It's absolutely mental how slow it is. So what you do is you retopologize the creature, right? Or this human sculpt here. So it goes from like a couple of million of polygons to between 10,000 to 400,000 polygons. So you save so many, you know, resources, and you get pretty much the same results. And it's all baked into different maps, right? Displacement maps and normal maps, and that kind of stuff. So it's the same thing here. So uh, if you have a duck like this, and it's like let's say this is kind of high poly, it's like 12,000 points. This is just, let's just say this is way to have it simulate. We could even like subdivide this twice. And this becomes like 205,000 points. This is so heavy to simulate, and I can't even use the copy to points because it's just way too heavy. So what we do is we have proxy geometries. Proxy geometries is just a geometry that is a lot more efficient, a lot more optimized than our hero geometry. So in Houdini, let's say this is our object. This is, after messing up a lot with this geometry, this is our high poly duck. we need to do something about this because we cannot work with this super high 200,000 points poly geometry. So what we do, we can use a poly reduce. It'll take a bit of time, but we can reduce this down to 20% polygons. You see, because this is a AI, it's not gonna properly retopologize your geometry like the original here is, but it will still maintain the shape of the creature or the geometry. It will still maintain as much as possible. All the areas that's more dense will be more dense than if not, depending on um, your settings. You can do preserve quads, so you kind of get somewhat a topology that somewhat works. Can reduce this even less. You'll still keep the details. I actually kind of like the quads. I'm gonna keep the quads down to 2%. It's a bit too little. 8% kind of works. So, so now we have like 16,000 points to work with. And if we run this through the copied points, it'll be so much easier to run the simulation or this animation, especially one pack. So we did this with the ocean simulation with the boats, where we had like a high poly. I think we did it though. We have like a high poly ship that we wanna simulate floating or just riding through the ocean. However, it's such a detailed mesh, and if you want to have water collide with the surfaces, the dock for instance, there's just going to be a lot of complicated stuff because of how the artist modeled the ship. It's just a whole mess. It's going to take so much time simulating this. So what do? Well, you can just have, for instance, a super low poly model of the ship. So like, for instance, here you have something that's high poly, and you just make it something like super low poly like this. And it's just to to simulate it, you're not gonna actually render this. So you get the motion of the boat, which is what's the most important, right? And you maybe get the water splashing, but that's all right. And then when you render this, you use the transformation information of the boat, but you slap this onto the point again. So you're rendering this boat, but you're only simulating this proxy boat. So if you don't quite get what I mean with that, just check out the previous lectures we had on this exact project. It was the flip simulation project. So yeah, um, the last question is, if you have like a scene with thousands of identical objects, how would you determine if they're copies or if they're instances using the information Houdini provides? We can actually use just make a project and just see how we can figure it out. So I'm gonna do the high field project we had, and I'm gonna just quickly build a mountain, which you can do with a high field distort by noise. So high field distort by noise will literally change the shape of, or it should, of the mountain. Wait, high field noise. It was, there you go. So high field distort will not change the shape of the mountain. It's not going to deform the mountain. It's just it's going to deform but not change the shape of the mountain themselves. But high field noise will. This kind of looks alright, to be honest. Oops. I can make this a bit more extreme or more subtle. I can make it look like a large scale mountain landscape. That's kind of cool. And then let's just build a bunch of trees. I think I actually have a tree here on my PC. Okay, let's quickly download a tree from TurboSquid. Hmm. Okay. Oh, excuse me, it's like 2 a.m. Jesus. Okay, that took some time. Oh, there you go. This tree has 64,000 polygons, and we're gonna make a landscape out of this, which is a little bit insane. So let's prepare this. So I'm just gonna scatter trees over the entire terrain. Because we don't really care about details right now, right? High field scatter. Oh, that's a low point. Holy smokes. 500 times 64,000. That's 32 mil. That's way too many. Let's do 20 trees. And let's just make them big. Okay, I think I have it somewhere in my downloads folder. Extract files. Yes. So I'm gonna use this tree model here. So what I'm gonna do is I'm gonna use a file. I'm gonna find the file downloads folder to this folder. That's a ginormous tree. Let's scale it down by like half. And then let's copy this to the points. Okay. There you go. So that's quite a lot of trees. It's pretty efficient though. Like we can have even more trees. Let's try like 50 trees. When we play the animation, it's kind of slow, but like think about it. That's 103,000 points, and we have 50 of the trees. So that would be 103,000 times 50. That's like 5 mil points, but we're still playing the animation pretty quickly. So one way to identify that these trees are actually instants is that we play the animation and it's pretty quick. We could also look at the node info here and see that, oh, Houdini actually automatically made these trees into just points, just instance trees, just by pressing middle mouse button here and seeing the point counts. We also see that the trees don't have colors, so that's a sign, but they don't have colors here either. We could test it out though. We make the trees green. Okay, they do have colors. That's a good thing to know. So yeah, um, I think that's pretty much the most straightforward way to figure it out. So yeah, if you find any other way to figure out if it's a instance or not, do let me know. And but yeah, just write it down in your report. So I'm sorry that this took like half an hour, but hopefully it answered your questions. So good luck and good night.